Bingham Canyon, Utah, July 1974, elevation 7,200 feet at the loading bench. The west ramp rises out of the pit at an 8.5% continuous grade for just over half a mile before breaking toward the primary crusher dump. At 1,400 hours on a Tuesday, the ambient temperature in the pit is 98 degrees Fahrenheit. A unit-rig Lectra haul M-200, a diesel-electric haul truck, is making the climb. It is loaded with fractured porphyry copper. The operator in the cab is one of perhaps 15 people on the Kennecott payroll who truly understands the thermal dynamics happening inside the General Electric motorized wheels mounted to the rear axle. The truck is moving at roughly 8 miles per hour. The diesel engine, a 1.6-cylinder prime mover, is screaming at maximum RPM to generate the electrical current required to move the mass against gravity. But the engine is not the limiting factor. The limiting factor is heat. Specifically, the heat building up in the winding insulation of the traction motors. The M-200 was designed for massive payloads, but the combination of altitude, ambient summer heat, and a sustained 8.5% grade creates an operating envelope that the manufacturer's specification sheet barely addresses. Inexperienced operators run the truck based on the rated payload and the throttle pedal. They push the machine until the thermal warning lights trigger or the motors cook. The experienced operator does something else entirely. They do not watch the warning lights. They listen to the pitch of the grid blowers, they feel the vibration through the deck plate, and they watch a single analog gauge on the dashboard, the ammeter. What exactly did an experienced Lectra haul operator know about reading electrical current on a sustained grade that prevented catastrophic motor failure? And why did the production supervisors silently allow them to carry less than the truck's rated capacity to do it? The unit-rig Lectra haul M-200 was officially rated for a 200-ton payload. That was the manufacturer's number, established under controlled conditions, near sea level, on moderate grades. At the Kennecott Bingham Canyon mine, in the summer of 1974, the documented average loaded weight of an M-200, leaving the primary loading benches on the west side of the pit, was 174 tons. This 2-6-ton discrepancy was not an accident, and it was not a failure of the loading equipment. It was a calculated survival tactic. Bingham Canyon's geometry is uncompromising. The porphyry copper ore body required deep excavation, resulting in a tiered amphitheater of benches and spiraling haul roads. When you take a 200-ton payload, add the empty vehicle weight of roughly 150 tons, and demand that the electric drive system push that 350-ton combined mass up an 8.5% grade in 9-8-degree heat at 7,200 feet of altitude, the physics become destructive. The GE traction motors relied on forced air cooling, but at altitude, the air is thin. It lacks the density to carry sufficient heat away from the motor windings. If an operator loaded the M-200 to its full 200-ton nameplate capacity and held the throttle wide open up the west ramp, the traction motors would exceed their thermal insulation class limits before reaching the top. The cost was winding degradation. Operating constantly at the thermal edge drastically reduced the mean time between motor rebuilds. So, the veteran operators and the shovel runners established an unspoken protocol. They short-loaded the trucks assigned to the longest, steepest pulls. They sacrificed 12 to 15% of the rated payload to ensure the truck survived the shift. Before we go further, if this kind of content is what you've been looking for, subscribe to the channel. Every video here goes into one machine class at one specific mine, what it was rated for, what it actually ran, and what the experienced operators knew that made the difference between the two. No trade show content, the documented operational reality. Understanding the operational limits of these early diesel-electric trucks reveals how American copper extraction relied as much on human instinct as it did on mechanical engineering. And leave a comment. If you operated or maintained unit rig Lectra Hall M-200S with GE motorized wheels on sustained grades above 8%, what was your specific physical indicator for thermal overload before the warning systems caught it? In a future video, we will examine how the transition to AC drive systems in the late 1990s completely changed the thermal limitations of downhill retarding. Now, back to the bench. How did the mine's dispatch system, which was entirely focused on maximizing daily tonnage, react to operators deliberately underloading the fleet's most expensive assets? The production target at Bingham Canyon was the ultimate competing force. The mine operated on economies of scale. To make low-grade porphyry copper profitable, the daily tonnage moved had to be staggering. The shift supervisors and dispatchers were measured purely by the tons delivered to the primary crusher. When a dispatcher saw an M-200 arriving at the dump carrying only 174 tons, the immediate instinct was to pressure the shovel operator to add another pass to the bed. However, the maintenance foremen were looking at a completely different set of numbers. They were looking at the cost per ton, and specifically, the severe capital expenditure of rebuilding GE motorized wheels. At Bingham, historical maintenance records from the period showed that the motor rebuild interval on trucks strictly assigned to the west ramp was approximately 30% shorter than on trucks running the shallower eastern routes. The veteran operators understood this financial reality intuitively. They knew that a burned-out traction motor meant a truck was off the bench for days, costing the mine far more in lost production than the 26 tons sacrificed on a single cycle. The experienced operator managed this clash between production pressure and mechanical reality by reading the ammeter. The ammeter displayed the electrical current draw of the traction motors. While it did not show motor temperature directly, current translates to heat. The veteran knew the specific amperage needle position that corresponded to the maximum thermal equilibrium of the motor on an 8.5% grade. If the needle climbed past that invisible, undocumented threshold, the operator knew the motors were cooking, even if the warning light remained dark. They would intentionally feather the throttle, backing off the speed to drop the amperage and let the grid cooling blowers catch up, explicitly sacrificing cycle time for component survival. They protected the asset while the dispatcher yelled on the radio for more speed. But what happens when the blast fragmentation is poor and the truck is forced to carry uneven, blocky material that shifts the weight distribution entirely to one side of the rear axle? Uneven loading was the hidden variable that destroyed traction motors faster than pure weight. The P&H 2100 electric mining shovels at Bingham Canyon were formidable machines, but their loading efficiency was entirely dependent on the quality of the blast hole drilling upstream. When a drill pattern failed to properly fracture the tough porphyry rock, the shovel operator was left dealing with coarse, blocky fragmentation. Loading this material into the bed of a Lectra Hall M-200 rarely resulted in a perfectly centered payload. If a massive boulder was dropped into the right side of the bed, the center of gravity shifted heavily. On a flat road, this was a tire wear issue. On an 8.5% grade, it became a thermal crisis. Because the rear GE wheel motors operate independently, the right rear traction motor was suddenly forced to do a disproportionate amount of the work to move the truck uphill. An inexperienced operator would simply apply power, oblivious to the asymmetrical strain. The veteran operator, however, felt the difference in the truck's handling immediately upon leaving the shovel. They watched the ammeter carefully, knowing that while the total combined current draw might look normal, the right motor was silently pushing past its thermal limit. There was no independent temperature gauge for each wheel in the cab of an M-200 inches in the 1970s. The operator had to infer the mechanical distress through the subtle vibration in the deck plate, the heavy lean of the suspension, and the sluggish response of the steering. To compensate, the veteran would adjust their line up the ramp, seeking the firmest footing to minimize rolling resistance on the overloaded side, and deliberately dropping their speed further to protect the struggling motor. This embodied knowledge, the ability to read the blast quality through the shovel load, and translate that into the thermal management of a specific electric wheel motor, existed entirely outside the unit rig operating manual. It was passed down verbally in the break rooms and observed from the jump seat during training shifts. But what happened to the mine's overall efficiency when the generation of operators who possessed this tacit knowledge began to retire, taking their undocumented thermal thresholds with them? When the generation of operators who possessed this tacit knowledge began to retire, the entire production system at Bingham Canyon felt the impact. The open-pit mining process is not a collection of independent machines. It is a tightly coupled, continuous flow system. The dispatchers in the 1970s relied on predictable cycle times to match the truck fleet to the shovels. When newer operators took the controls of the M-200S on the west ramp, lacking the physical feel for the motor thermal limits, they created a systemic ripple. If a new operator drove aggressively, relying solely on the truck's rated capacity and the throttle pedal, they inevitably triggered thermal overloads. The truck would either automatically derate its power, crawling to a near halt on the grade to cool the grids, or the motors would fail outright. Either scenario destroyed the cycle time. Conversely, if a new operator had been warned about the grades and drove with excessive caution, feathering the throttle too early and running far below the optimal amperage threshold, they artificially extended the haul cycle. In both cases, the truck did not return to the loading bench when the dispatcher expected it. The massive P and H 2000 100 shovels, with their immense capital operating cost, were left sitting idle, waiting for a truck to arrive. A 40 cubic yard shovel digging air destroys the shift's economics instantly. The M-200 was no longer just a struggling truck, it had become a bottleneck for the entire mine. What exactly did the maintenance crews see when these thermally abused trucks finally limped off the bench and into the shop? When an M-200 limped into the Bingham maintenance bay, the mechanics did not need the operator's shift log to know how the truck had been driven. The General Electric 772 motorized wheels told the exact story. The mechanics saw the immediate physical cost of lost operational knowledge. Stripping down a traction motor revealed the precise nature of the thermal abuse. The mechanics looked directly at the commutator bars and the state of the winding insulation. If the insulation was brittle, charred, or flaking away, it meant the motor had been run constantly above its thermal class rating. The exact scenario the veteran operators avoided by feathering the throttle and reading the ammeter. A burned-out traction motor was not a field repair. It required the truck to be parked in the heavy maintenance bay, lifted by massive overhead cranes, and stripped of its rear duals and planetary gears just to extract the motor assembly. This represented days of downtime. To fight this escalating failure rate, engineers attempted mechanical retrofits. They tried increasing the capacity of the grid cooling blowers, attempting to force more high-altitude air over the electrical components to compensate for the aggressive driving habits. But increasing blower speed drew more parasitic power from the diesel engine, marginally reducing the power available to climb the 8.5% grade. Mechanical patches could not replace the veteran operator's intuitive throttle control. The hardware had reached its absolute physical limit in that specific environment. How did mine management attempt to engineer their way out of this human factor bottleneck when mechanical upgrades failed to solve the heat problem? If the operators could no longer manage the 8.5% grade thermally, the engineers had to reconsider the very geometry of the pit. They began attempting to ease the ramp profiles, trying to reduce the climbs to 8% or even 7.5% where the rock mechanics allowed. However, Bingham Canyon's steep, hard rock walls severely limited how wide and shallow the haul roads could be cut without stripping millions of tons of unprofitable waste rock just to create the angle. The geometry of the earth proved harder to change than the machines. Consequently, mine operators went back to manufacturers like Unit Rig with a clear mandate. They needed trucks with greater thermal mass. They demanded drive systems that did not rely on the undocumented finesse of a veteran driver to survive the shift. This pressure drove the rapid development of the larger 240-ton and eventually 300-ton class vehicles in the 1980s. These newer trucks featured significantly larger wheel motors, advanced cooling architectures, and control cabinets designed to handle higher sustained amperages without instantly baking the insulation. But modifying the truck fleet created a cascading engineering problem. A larger truck requires a wider haul road to safely pass another vehicle. It requires a larger primary crusher hopper to accept the increased payload without spilling, and critically, it required even larger electric shovels to load the truck efficiently in 3 or 4 passes. A change in the thermal capacity of a traction motor forced a redesign of the entire extraction geometry. As the 1980s progressed and the fleet expanded, what technology ultimately replaced the raw, physical feedback of the M-200's deck plate? Early computerized fleet dispatch and digital monitoring systems arrived to replace the missing operator instinct. By the late 1980s, the industry was moving toward systems that actively monitored payloads through strut pressures and tracked motor temperatures electronically. The silent dialogue between the veteran operator's foot and the ammeter was being replaced by algorithms that governed the engine and warned the operator long before thermal limits were breached. This technological shift marked the beginning of the end for the Unit Rig Lectra Hall M-200 fleets at Bingham Canyon. The newer generation of trucks, transitioning toward the massive AC drive electrics of the late 1990s, could hold dynamic retarding loads going downhill and sustain massive amperage going uphill without baking the grids or cooking the traction motors. The machines no longer required the operator to intuitively protect them from themselves. The onboard computers handled the survival parameters, leaving the operator to simply steer and manage traffic. This transition fundamentally changed the nature of the job. The deep, embodied knowledge of reading a blasted face for load distribution or feeling the subtle vibration of an overheating right rear wheel became largely obsolete. The dispatch systems optimized cycle times mathematically, removing the human variable that had previously saved the motors but disrupted the flow. As the new, larger, sensor-laden trucks took over the primary ore routes, the aging M-200s were pushed to the margins of the operation. What did the final, undocumented days of the M-200 fleets at Bingham Canyon actually look like before they were completely erased from the active roster? The final days were defined by cannibalization. As the M-200s aged past their optimal economic life in the late 1980s, Bingham Canyon, like many American pits, relegated them to secondary duties. They were assigned to haul waste rock to the upper dumps, where the grades were less punishing, or they sat in the ready line as spares, only fired up when the primary fleet went down. When a traction motor finally failed catastrophically on a high-hour M-200 chassis, the truck was no longer sent to the heavy maintenance bay for a rebuild. The capital expenditure could no longer be justified against the truck's remaining operational lifespan. Instead, it was parked at the far edge of the maintenance yard. It became an organ donor. Mechanics stripped it for alternators, grid blowers, suspension struts, and planetary gears to keep the dwindling remainder of the fleet running just a few months longer. The precise thermal limits, the specific way a certain chassis pulled slightly to the right under a heavy load, the exact vibration that preceded a grid failure, all the granular details known by the veteran operators became irrelevant as the machines themselves were dismantled. The physical hardware was slowly erased from the bench. The dispatchers stopped calculating M-200 cycle times. The shift supervisors stopped arguing with maintenance foremen about short-loading the west ramp because the new AC drive trucks could pull the 8.5% grade at full capacity without breaking a sweat. Where does that hyper-specific, hard-won operational knowledge reside today? The last unit rig, Lectra Hall M-200S, in active production service at Bingham Canyon, were retired in the late 1980s. The machines went to scrap, to parts suppliers, or to the few smaller mines that kept running older equipment to the end of its mechanical life. What the maintenance records showed about how they had been operated, which machines had been managed well, which hadn't, what the experienced operators had done differently, went with the operators when they retired. Some of it was written down, in the form of informal shift notes and maintenance observations that someone thought to keep. Most of it wasn't. If this video gave you something real, subscribe. More machines, more mines, more of the operational reality that the trade show brochures never contained. Understanding these early diesel-electric haulers is essential for documenting how human judgment bridged the gap between mechanical limits and industrial demand in American history. And if you ran one of these unit-rigged trucks, worked on the P&H shovels that loaded them, or engineered the ramps at Bingham Canyon, tell us in the comments. When you lost a traction motor on a grade, what did the teardown actually reveal? In the next video, we will examine the shift to the 300-ton AC drive class and how it completely rewrote the rules of downhill retarding. The most complete operating manual for these machines is in the heads of the people who ran them. Most of it was never written down. The ramp is still there. The grade is still 8.5%. The trucks that run it now are twice the size and know nothing about what was learned on it.